When working with microcontrollers, it is quite common to have to interface with other ICs and devices. There are several different ways for our microcontroller to communicate, such as to a PC over USB or directly powering a 7-segment display's pins. However, the most efficient use of pins seems to be using a serial method of communication, such as SPI or I2C. In fact, many of the AVR microcontrollers use SPI as a method for programming. However, in this video, we will be covering the I2C, how we can use it, and what it is good for. And ultimately, we are going to use it to interface with a real-time clock for accurate timekeeping. Let's get started. Before we start making the clock itself, let's fully understand how the I2C protocol works. First, let's understand what it can and cannot do. It allows us to have up to 112 devices on the same 2-wire bus while using 7-bit addressing. We are also able to have several masters on the same bus controlling the same slave devices. Each slave has an address so that the master can select which device it wants to interface with. The DS1307 RTC, for example, has an address of 68 in hex. The 2-wire bus is made up of both the serial data and the serial clock lines. Both of these lines should be pulled up with resistors anywhere from 2K to 10K. Personally, I chose 5K resistors. Now, let's explain how the master actually uses these two lines to select and interface with any device. First, the master will let all of the slaves know it is ready by giving a start condition, which is basically when the SDA line goes low while the SCL line is still pulled high. Then, the master starts generating a clock, usually about 100 kHz, on the SCL line. The master will then give the address of the device it wants. Using the DS1307 as an example, it has an address of 67 in hex. Then the master will indicate whether this operation is either a read or a write. The 9th bit is then the acknowledge bit. Basically, the device that is receiving will pull the data line low if everything is okay. Otherwise, it will stay high and end up as a no acknowledge, meaning that the transmission is over and the master needs to decide how to proceed. Now, depending on whether a read or write was sent, the slave will send data to the master, or the master will send a slave an address to write to. Then data is sent between both until the master generates a stop condition, which is just when the clock line is high and the data line goes high. No other devices can use the bus until a stop condition is generated. Using this knowledge, let's give an example exchange between a microcontroller and our DS1307. First, the microcontroller generates a start condition and then gives the address of 68 in hex. In this case, we will be reading, so the microcontroller outputs a 1 for read. The DS1307 acknowledges and starts running from its timekeeper memory, starting with the memory stored with seconds, and then the master acknowledges when it receives that data. The DS1307 then sends the next byte, which in this case is the minutes data, and master again acknowledges, and so on and so forth until the master sends a non-acknowledge over the data line. The master then sends a stop condition to signal that the transmission is over. Now that we understand how to interface with these I2C devices, let's design an accurate clock using the DS1307. This IC is an RTC, also known as a real-time clock, and it keeps accurate time based on the crystal oscillator's frequency. We could simply use a microcontroller's hardware timer to keep time, but it isn't as accurate as an RTC, nor will it keep track of time while the main power goes off. However, the RTC isn't 100% accurate either, but it is close enough to function as a usable timer with adjustment every few months. It also features the use of a small battery to power it in the case of power loss. That means if your power goes out, it will still keep track of time so that you don't have to reset it when the power is restored. In the battery mode, it uses a measly 500 nanoamps of current, meaning that you can run it in this mode for several years. Now, we need to pick the microcontroller and output method. For this project, we will be using the Atmega AA microcontroller along with this blue 4-digit 7-segment display. I connected the display to the microcontroller first, just so that we had some output. Basically, we can select each digit by outputting a logic 1 on the anode pins. Then we sync the current on any of the segment pins. If we select a different digit, we can quickly switch through them all so fast, it seems as if they're always on. If you're still unsure of how connected to this display, here's the display schematic. Also, if you haven't already, feel free to check out my video on multiplexing because it goes into greater detail on how multiplexing actually works. After setting up the display, I wired up the DS1307 with a 32.768 kHz crystal to my microcontroller. Luckily, the Atmega AA already comes with the hardware I2C support, although they call it TWI or two-wire interface in the datasheet. So we can connect the SDA and SCL pins directly to each other. Also, don't forget to add the pull-up resistors to these pins because they are all open drain. After writing the code on the microcontroller to read from the RTC, we can see that it is working. For this project, I will be using 24-hour time to remove the need for an AM and PM indicator. However, we still need a way to adjust what time it is just in case the clock is wrong. And for that, I added a button that will quickly add time to the timer. The result from that button press is then written to the RTC's memory. After proving the circuit works on our breadboard, we can then solder it together onto a prototyping board. The most difficult part of soldering something like this is the display, just because of the sheer number of connections that need to be made. However, the microcontroller and the RTC are both very simple to wire up because of the simplicity of the two-wire I2C protocol, so these shouldn't be a problem. After some time soldering, this project is mostly complete, and we can see that it works mostly as expected, except for one thing. I added a coin battery to the VBAT pin on the RTC, and now it works as expected, and the clock remembers what time it is even when we unplug it. Now that we have finished the project, let's talk about some possible improvements to the timekeeping aspect of the clock itself. You can replace the DS1307 with its superior cousin, the DS2321. The DS2321 is much better than the DS1307 because of its internal temperature compensated oscillator, meaning that it can keep accurate time up to the minute for over a year, whereas the DS1307's external oscillator will change depending on its environment, possibly causing it to drift significantly over time. Anyways, I'd say that the clock turned out well and it looks great on my desk. You should build a project like this if you're looking to learn more about I2C and real-time clocks. If you enjoyed the video, please consider subscribing to see the other videos that I create. Have a good one.